All right, today we're going to learn about dynamic equilibrium. So this is today's lesson. Just want to recap on some basic vocabulary that I hope everybody already knows before I dive into dynamic equilibrium, and that is vocabulary that has to do with states of matter. If I have solid here, liquid, and gas, what do we call going from solid to liquid? That's called melting. What do we call going from liquid to solid? Well, that's called the opposite, freezing. What do we call going from a liquid to a gas? Well, that is not evaporating or evaporation, as evaporation is a process of going from liquid to gas below the boiling point. But at the boiling point, we call this vaporization or boiling. What's the opposite process called? It is called condensation. And then what do we call going from a solid to a gas? This, I'm sure some of you have seen it. It's a process going from solid to gas without going through the liquid phase. So you skip the liquid phase, and that's called sublimation. And a very common example is dry ice. What's dry ice? It's frozen CO2. So usually it's put at a very, very low temperature to the point where it solidifies. But as soon as you expose it to the room conditions, well, it goes to the gas right away, because CO2 under room temperature, atmospheric pressure, is a gas, so it sublimes right away. So that's a typical example of sublimation. What is the opposite process of sublimation? This is less commonly used. It's called deposition. All right. So I had to go through this because I'm going to use a lot the term condensation when I talk about dynamic equilibrium. So in a previous video, I did talk about the process of evaporation in open containers. So in this case, with dynamic equilibrium, things are going to start pretty much the same. And I'm going to assume that my liquid here is water. And the only difference is that the container is now closed. It has a lid, so it's tightly closed. So what happens is the same thing as what happens with evaporation in the beginning. So again, you have these particles here on the surface, and you have water particles in the middle, and those that are in the middle are surrounded by other water molecules, so there's a lot of intermolecular forces. So these are not going to be the first ones to leave, but the first ones to leave are going to be the ones on the surface, because they are only exposed to half of the intermolecular forces, and the other half is free. So it is enough to get some energy from the surrounding. Let's say the surrounding is at room temperature, which is typically 25 degrees Celsius. And then this energy is going to be enough to allow some of these particles to escape, exactly like the process of evaporation in an open container. The only thing is, where are these particles going to go? Are they going to go too far? Well, not really. The farthest they can go is probably up here. It's going to have droplets of water, and eventually with time, these droplets are going to just become bigger and bigger. And instead of having water vapor, now we have water droplets. So water is condensing, and it's going to get, after a while, a little heavy, that it's going to fall back down in the container. So that's really the big difference. So you start with in the beginning, as soon as you open the container, evaporation is going to start going up. But then, because particles are falling back in, that process of evaporation is going to stabilize. Okay? It's going to stabilize. So this is where we talk about dynamic equilibrium in this area right here. So dynamic, what's the opposite of dynamic? Static. So dynamic means that there's always constant motion. And equilibrium means that we reach a state where things seems to not change. And you see here that we have a straight line, nothing changes. So what happens is, in the beginning, I might have 10 particles that are going to evaporate, and then 100, and then 1,000, until I am getting particles here that are going to condense back in. So I will always have 1,000 particles evaporating and 1,000 particles condensing. So I'm going to reach that state where both evaporation rate and the rate of condensation is the same. So in a dynamic equilibrium, rate of evaporation equals the rate of condensation. And let me give you an example from the real life. Let's say I have here in in Southern California, I have OC, Orange County, and I have another county next to it, which is LA County. Okay, so let's assume, these are numbers off of the top of my head, that LA has 8 million people, and that OC has 3 million people. And let's say it's been like this for the last 5 years. Again, this is off of the top of my head. Does this mean, well, this means if Orange County has had 3 million people and LA has had 8 million people for the last 5 years, and the numbers don't change, well, that is equilibrium. But does it mean that no one is commuting or moving between LA and OC? Of course not. It's not always the same 3 million people here, and it's not always the same 8 million people here. There are people going back and forth. So there is an equilibrium, yes, but there is also commuting between the two counties. There are people moving in and moving out. So there is a dynamic. This is why we use the term dynamic. The particle that condenses over here is not always the one that's up here, but it can go back into the water, and it's going to be replaced by another one later. But the overall, the net, seems that there is no change and that the numbers are the same. That's really what dynamic equilibrium is about. Okay, so dynamic equilibrium means that there is motion. The particle that was once condensed is going to be now evaporated, or is going to be in the water itself. It's going to keep changing, but the overall does not change. Okay, so that's why we have this plateau here, or this steady state here. All right, so that's for dynamic equilibrium. All right, and that's it for today.